Cool. All right, I have drawn up here what we had at the end of lecture last Wednesday that I had intended to get through, but we ran out of time. So as a refresher, we have an RC circuit. So that's the common phrase for a circuit with a single resistor and a single capacitor. As the input to that circuit, I have a step change in voltage. Okay, so the input voltage goes from 0 to some constant V in at time t equals 0. I didn't draw there, so that happens at time t equals 0. I want to get V out as a function of time. Okay, and I kind of wrote down all of the equations we know. I know Ohm's law applies to the resistor. I know the capacitor equation, which as far as I know isn't named after anybody. It's just the capacitor equation, I equals C dV dt. I know Kirchhoff's voltage law and Kirchhoff's current law apply to anything, not just resistors, right? So if two things are in series, whether they're resistors or capacitors, the currents have to be the same. If two things are in parallel, whether they're resistors or capacitors, the voltages have to be the same. I also remember my crash course review from differential equations. If I have a first order linear ODE of this form, tau times dx dt plus, my handwriting's awful, x of t equals k times some constant f of t, or in this case that f of t is this step input, this constant voltage. I know that the solution to that differential equation is x of t equals x naught, which is my initial condition, minus x of infinity, which is my final or steady state condition, times e to the negative t over tau plus x of infinity. Okay, went through that kind of quickly, but again, we wrote all of that down last time. Okay, cool. Given all of that, I just wrote a bunch of equations down. Find the differential equation for this circuit. We're going to do this as a multiple choice poll everywhere. Okay, I'm going to activate this in a second. So, given all of the things you know, and there's probably more than one path to kind of do the algebra to arrive at the correct answer here, but go ahead and find the differential equation. So again, not the solution to the differential equation. Find the differential equation of this form. So tau is some constant, but you're going to have the general things here. So tau and kf, you're probably going to have values from the problem plugged in. Okay, we're not using numbers. It's not, we're keeping it symbolic with R and C. It's not 10 ohms or whatever. Find that differential equation.
I'm still trying to connect it here.
Well, so, okay. We're trying to find a difference for this circuit. We know. Yeah, well, if I do like process elimination, this form is how it's out. Yes. So I'm going to say that it's probably out. Yes. And then there's one of them multiplied by RLC, and one multiplied by C. There's no, what's confusing?
There's no x.
No, we're not doing, we're just finding the different words. No, but x is equal to some do you see above where it says dV dt, I is C dt? My thought is, we're saying V on one side, is equal to our RLC, so I would say option.
Yes.
Can I ask you a question?
Yeah, 1 second, although I heard a question already, so let me clarify something. X can be anything. right? So this is the generic form of this equation. This could be a mechanics problem where X is literally position. In a circuits problem, X could be voltage, it could be current. I think I heard somebody ask, like, wait a minute, there's no X. Okay, so you can substitute another variable. Remember, we're trying to solve for V out, so like, hint, hint, X is probably V out. Okay, was that your question, or did you have something else? Did you have another question, or was that your question?
Yes. My question is for everyone just call my name.
Sorry.
So scared. I was like, oh no.
Deep breath.
So for the thing on the left, we're taking the differential equation of it with respect to t.
Yeah, sorry, that should be, this is my crappy handwriting. That's a dx dt.
Okay.
That's a dx dt. This is an x of t. That's f of t. Again, and then over here we have t and tau. I'm trying to differentiate kind of the t and the
right. So
tau there.
From my understanding of how to approach it is to take that, you plug it in on the left, and then you solve for dx dt. Is that what you're saying?
No, so I am saying, right now, pretend that's not there. I want you to find this for that circuit, given what you know about circuits. So this isn't a mechanics problem. We don't have F equals MA, right? We have Ohm's law, the capacitor equation, and KVL and KCL.
Okay, so then would it, using the I equals C dV dt, that's the equivalent of dx dt. So this top circuit X would be V, right?
Sorry, say that one more time.
In the differential equation that we're creating,
Yes.
our X is voltage.
Yes.
I changed my mind, guys. I think it is.
Okay. We are at around 113, 115 replies. So I'm going to close this out and work through 117. Okay, let's go back to the previous question. Responses, correctness. The correct answer to the previous question, which about 40% of you got right, was the last option. So I think that was E, because there were 5 of these. So I am going to go through the derivation for this, because again, this is kind of nebulous about what it was asking me to do here, and maybe the procedure wasn't that clear. So, yeah, right now I was just asking you to find the differential equation, because we just take for granted that that is the solution of this differential equation. Okay, this isn't a differential equations class. So, to find this differential equation, I'm going to look at this circuit and go, okay, what do I know? What can I apply to this circuit given all of the physical laws I know? Well, this is a series circuit where I have the resistor in series with the capacitor. So I know their voltages are going to add, and after that step input voltage is changed, they're going to be equal to the input voltage, right? So right off the bat, I can write down an equation using KVL that says the voltage, I'm going to use V sub R to mean the voltage drop across the resistor. So that is the voltage drop between there and there. Remember the difference between asking for the voltage at a point, which is implied reference to ground. I see people with phones out, so if you're texting your friends that they're in trouble, don't do it. You don't want to get roped into it. Remember the difference between asking for the voltage drop across the resistor, which is not connected directly to ground, and the voltage drop across the capacitor, which is connected to ground. So in this case, asking for what is V out and what is the voltage across the capacitor, or what is the voltage at that point with the implied relative to ground, those are all the same thing. Okay? I know the voltage drop across the resistor, is in series with the voltage drop across the capacitor. If I add those up, after that input voltage is changed, they have to be equal to VA. Right? I know that I want a differential equation in terms of VC here, right? Because VC, again, whatever I call it, VC, V out, voltage drop across the capacitor, those are the same thing. So V in is a constant, but I don't know VR, and ideally I want to get a differential equation in terms of just one variable VC, right? So I can plug in Ohm's law for my resistor. So I have IR plus VC equals VN. That didn't really help because now I've just switched variables. Now I know R is a constant, but I is some other variable that I don't know, so I still have a differential equation with 2 variables in it. But here is where, let me grab a different color, Kirchhoff's current law comes in handy. These are in series, and again, Kirchhoff's current law applies regardless of whether it's a resistor or a capacitor or whatever, so I know those currents have to be equal, right? The current through the resistor has to equal the current through the capacitor. Current through the resistor is VR over R. Current through the capacitor is my capacitor equation, C dVc dt, and both of those are equal to I. Right, so I can plug, and notice Vc is the variable I want. I can plug that in for the I over here, and then I just get RC d. I'm going to switch back to V out. Again, I'm not being consistent about the notation, but dV out or dVc, either way, plus V out of t equals V in, and there is my differential equation, which is kind of in the same format as this one, except instead of a tau there, I have RC. So my time constant for this circuit is RC. Now, again, for people who took system dynamics, remind me, you did step response and time constants for a mechanical system? Okay, so time constant is not a totally new concept here. See for me? Okay, so time constant of my first order RC circuit is RC. What does that mean? Some notes. So sorry, I think I actually drew this graph last time, but as a quick reminder, we have our graph with time on the x-axis and output voltage on the y-axis. That input changes from 0 to Vn at times t equals 0. And then the response or output voltage kind of looks like that. So you think of the capacitor charging up, and it's going to get about 63% of the way there in one time constant, which equals RC. So if I increase either R or C, that time constant gets longer and it takes longer to charge, which kind of makes sense. I think intuitively, if you think like a bigger capacitor is, that more capacitance is going to take longer to charge up to the same voltage. Or if you put a bigger resistor in there, less current is flowing, so it's going to take longer to charge up. Okay, so that was just finding the differential equation, but that doesn't give us this equation, which is what gives us the actual shape of this curve that you can plot and what you're going to do on homework 3, right? So if we want to do that, we need, again, our initial condition, use a million different colors, and final condition. Okay, so we know our initial condition, the input voltage is 0, so everything is just 0, the voltage across the capacitor is 0. So the initial V out is also just going to be 0. And then V of infinity. My high school calculus teacher would hate me for this because you're supposed to write limit as V, t approaches infinity or whatever, not V of function infinity. So apologies. I think he's still alive, so I'm not going to say he's rolling over in his grave, but he would be really mad at me if he saw me doing this 20 years later. But wait, I'm a lot older than that, whatever. That's how I write it, whatever. That's what it means. V of as time approaches infinity, steady state, whatever you want to call it, is going to approach V in. And again, this was that concept test question where, again, voltage across an open switch or a capacitor, which we treat like an open circuit. Okay, so we know our final condition. Sorry, we know our initial condition. We know our final condition. I don't have a third color pen, but we also know tau. That was the whole point of finding the differential equation, was so we could find the time constant tau, right? And this simple circuit, where we happen to have a single resistor and a single capacitor, it works out to just be RC. But you can imagine if you had some more complex circuit with more resistors, R1, R2, capacitors, C1, C2, you could, if it winds up being a first order circuit, you could do this and find a different time constant. Okay? So knowing all of those values, and tau equals RC, we can then rewrite it like this. So V out of t equals our initial condition, which is 0, our final condition, which is Vn, times e to the negative t over Rc, plus final condition, which is Vn again. It's a little awkward to have it written like that, so you can kind of do a bunch of algebra and just rearrange it. So Vn times 1 minus e to the negative t over Rc, right? So that's crossing out the 0, factoring out the Vn, and then writing it as 1 minus this term instead of having the Vn in both terms. And that's a little more intuitive because you see you just have some constant times this in parentheses, which is 1 minus a decaying exponential, right? So this term gets smaller, and so as you're subtracting off a smaller term from some constant, then eventually as t goes to infinity, this term goes to 0, and you just get Vn. Cool. You never have to do that derivation again in your life, right? The point is, when you go or asked to go plot this on homework 3, there's your equation, right? Like you are going to be building a physical circuit with a resistor and a capacitor, and you are going to drive it with a function generator. So your oscilloscope, which I haven't really talked about much in lecture yet, it can actually do two things. It can measure a voltage against time, so it can give you this graph, but it can also generate an output voltage. So you can tell it generate a square, I forget all the options, but like generate a triangle wave. So triangle, actually I think that's what a saw, I forget, I actually need to go look this up because I'm getting them mixed up in my head. One of these is called a sawtooth wave, and one of them is called a triangle wave. I think I might have mixed them up right there. You have square wave, and of course you have sine wave. So your function generator on the oscilloscope can generate all of those, and you can do things like adjust the amplitude and frequency, feed them into a circuit as an input. So in this case, modeling kind of a constant step input is kind of like just that part of a square wave, right? So when I say, okay, I just have to go from 0 to some constant, if you have a low enough frequency square wave, it's just kind of like having a single step input. So point being, you're going to have all the parameters for this. You're going to have the amplitude of that for Vn. You're going to know R and know C. You can plot what that graph should look like theoretically, but then you can also measure the actual graph with your oscilloscope and then compare the theoretical to the experimental graph. So kind of a classic lab that, again, used to be done in person. Now we're doing it with the individual, used to be done as a group. Now we're doing it with the individual kits, so everybody actually learns how to use an oscilloscope. The motivation for that being that the oscilloscope is a very useful debugging tool later in the semester when you're using the Arduino. Okay, so there are multiple either sensors or Arduino pins that are supposed to output some wave. For example, we're going to talk about this much later in the semester, but kind of a preview. A square wave is actually how you control the speed of a motor. Okay, so the Arduino has digital pins that can only be on or off. They cannot output a voltage halfway in between. So if you want your motor to only go 75% speed, you can't output 3.7 volts or whatever 75% of 5 volts is, but you can turn the pin on and off really fast. It's kind of like the same as how some LED light dimming works. Rather than actually changing the current through the LED, it just flickers them on and off much faster than we can see, and the result to human eyes is that it just looks dimmer. Okay, same concept for controlling the motor. But you have all that set up and your motor's just not spinning and you don't know why. One of the first steps is you take your oscilloscope and you go, okay, is my Arduino pin actually generating the square wave? Again, as I mentioned this, I think way back on day 1, we can't see electricity, so we have no idea, without hooking the oscilloscope up as a visualization tool, if the Arduino is doing what it should be doing. So when you were sitting there Friday night, hating me because you hate using an oscilloscope and you didn't listen to me and start the homework earlier than Friday night, remember that that is the motivation to make your life easier later in the semester. Okay, this is a useful tool for getting your gosh darn robot to work. Okay, so try to remember that when you're kind of in the trenches doing homework 3. Okay, questions on that whole derivation or kind of the equation we wound up with? Good? Okay. Let me remember what we're going to do next. All right, so far we have talked about capacitors quite a bit. We're also going to talk about inductors, which I should have but didn't really prepare a poll everywhere question for, just to give me a sense of how well people remember this from physics. Raise your hand if you think you remember inductors equally as well as you remember capacitors from physics. Okay, so Alma and I remember, I was, for whatever reason, when I took high school and then undergraduate physics, like we talked about capacitors a lot, but then didn't really talk about inductors at all. So did you not cover inductors at all in physics, or you did, but you just don't remember them as well as capacitors?
Never heard of this before.
Never even heard of inductors before. So people who took 2213, you didn't even talk about inductors at all? Did? Some disagreement? Okay. Raise your hand if you remember learning about inductors in 2213. Okay. So okay. Raise your hand if you've never heard of an inductor before. Okay, so a few of you, so that's all right. We're all going to get on the same page here. Okay. So, inductor. Circuit symbol for an inductor is, did somebody say, this thing, squiggly line thing? No? Okay, does this look familiar? So it's not a resistor. So this is, again, with my crappy handwriting, you're going to have to be careful. It's not the zigzag of the resistor. It's kind of curly or loopy lines, which is physically representing a coil of wire. Okay, and inductance is referring to the property. Here's hopefully jogging your memory from physics. Remember how even a straight wire has a magnetic field around it, right? You can do right-hand rule, or if you have current flowing through a wire, point your thumb in the direction of the current and your fingers curl in the direction of the magnetic field, B, yada yada. And then if you have a whole bunch of loops of wire, you kind of do the right-hand rule around that whole thing, and you wind up with a much stronger magnetic field going like this. Okay, all of that hopefully look familiar from physics. So there's some equation for like the strength of the magnetic field based on the number of turns and the current, yada yada. We don't care about that in this class. We just care that this has inductance, which is measured in a unit called henries, abbreviated H. Kind of like with farads, a henry is a pretty big unit. So for something like a small motor like we're going to have in this class, again, I think the inductances are maybe more on the order of like dozens or hundreds of millihenries, not megahenries or kilohenries or whatever. Just like with, and sorry, let me back up. The reason we care about inductance primarily in this class is motors. Right? Motors have coils of wires inside them, and coils of wires have inductance. So while you can also go buy just an inductor, just like you can go buy a capacitor, your kit can have a capacitor in it, you may build a circuit that has an inductor in it, although if you do stuff like crack open a power adapter like I did a few lectures ago, usually you're going to see plenty of capacitors and resistors in those, usually not as many inductors. Our reason for caring about inductance in this class, in a mechatronics class, again, is motors. Motors have inductance because they have coils of wires inside them, and there are kind of some special considerations you need to take to protect the circuit from voltage spikes introduced by driving an inductive load. And we'll talk about that more later in the semester when we get to controlling a motor with an Arduino. But kind of as a preview, and again, I think using mechanical analogies helps here. Think of inductance like mass. And we talked about, you can think of kind of resistance kind of like friction. You can think of a capacitor kind of like a spring that can store energy. Think of inductance like mass that can store energy, but instead of in stored charge on parallel plates like a capacitor, it's storing energy in that magnetic field. And I'm talking about protecting a circuit from other things. Think about what happens when a mass stops suddenly, right? Stuff breaks. You have a very large force when a mass suddenly decelerates. Similarly, as we'll see in a second with the equation, when you shut an inductor off suddenly, so if I have an inductive load or a motor running on a switch and I open the circuit all of a sudden, I open the switch and I try to stop the current flowing through the inductor, that's the equivalent of stopping a moving mass to the wall. Okay, so that can create a big voltage spike and sparks and do bad things to your circuit. So we'll talk about how you deal with that later in the semester, but again, that's the motivation, not just kind of learning physics equations for the sake of learning equations. So kind of like, although speaking of equations, we had an equation for a capacitor, We also have the equation for an inductor that's kind of reversed. So we have V equals L di dt. The capacitor one was I equals C dV dt. Again, as far as I know, this equation is not named after anybody. It's just the inductor equation, or whatever you want to call it, where we are using the letter L for inductance. Just like with a capacitor, we have rules for steady state and continuity that are kind of based on, or you can derive from this equation. So in steady state, so steady state means nothing changing. My derivatives are 0. If di dt is 0, then my voltage drop across the inductor is 0. So in steady state, an inductor behaves like a short circuit. V goes to 0. And again, think of it kind of like a mass that's kind of like, an object in motion remains in motion, right? Like in steady state, a mass just keeps going with no required force, right? So in steady state, the inductor just kind of acts like a short circuit with no voltage drop across it. And for continuity, current must be continuous. And then that is coming mathematically from this equation that says, okay, if you have, and someone was confused about how I drew this last time, if I have a jump in current like that, then this derivative is infinite, which would require infinite voltage. Okay, so mathematically, that says you need infinite voltage. And what happens physically is if you have current flowing through an inductor and then you open a switch so that current suddenly drops to 0. So if I have this, right, I have some constant current, I open a switch, and the current goes down to 0, that gives me a huge negative derivative here, which gives me a huge kind of inverse voltage spike across the inductor, which again can cause bad things to happen to the rest of the circuit. Okay, so again, for the few of you who maybe hadn't seen this at all in physics before, kind of like a capacitor in that it can store energy, but it's storing energy in a magnetic field as opposed to in an electric field, has a different equation. So we can it helps to have all of this maybe summarized in a single little table in your notes, and this is also on Canvas. It's kind of its own little PDF, but if you have a table for example, a part, you have resistor, capacitor, and inductor. The variable you use, so we have resistance R, capacitance C, and inductance H. The unit, ohms, abbreviated omega, farads, abbreviated capital F, henries, abbreviated capital H. You have an equation for each one, so V equals IR, I equals C dV dt, and V equals L di dt. You have a continuity rule that doesn't apply to the resistor because the resistor doesn't have a differential equation, right? Ohm's law is just algebraic. For the capacitor, you have voltage must be continuous. For the inductor, you have current must be continuous. You have a steady state rule, which again doesn't really apply to the resistor because it's not a differential equation. Steady state for a capacitor, the current goes to 0, so it's like an open circuit. Steady state for the inductor, you have the voltage goes to 0, so it's like a short circuit. And then you have a physical analogy for each part. So for a resistor, you think about it like a damper. Again, if you took system dynamics and you remember your spring mass damper system. For the capacitor, you think of it like a spring. And for the inductor, you think of it like a mass. Okay, so again, these are kind of your three, you might see them, if I say in lecture or you see in a textbook or something, passive components. These are the three things we're talking about. So you just, again, you never need to derive those equations again, or we don't care about kind of the origins of them in physics. That's just the equation you look up for each of those parts. Let me figure out how much time we have left and what I want to do. Okay, I know that was a lot of writing, so I'm going to give people a second to copy that down as I get started with my next page here. Yes?
What does it say in the flow physical
Damper. So technically, a damper where the analogy to system dynamics, where the damping force is proportional to velocity, as opposed to Coulomb friction, which is just a constant, basically the weight of a sliding object. So when I've been saying a resistor is analogous to friction, that was a little hand wavy. It's more mathematically more accurate to treat it as, again, if you took system dynamics and think of a spring mass damper system, and RLC circuit, which we're going to talk about in a second, is pretty much mathematically exactly like a spring mass damper system. Okay, so speaking of spring mass damper systems, again, if you didn't take system dynamics, I'll try and talk about a more intuitive explanation for this in a second, but the classic example you see where you have a mass on a roller attached to a spring and a damper, right? And if you didn't take system dynamics, I wish I had brought one, but I forgot. Think of like a slinky, right? If I just hold a slinky and it has some springiness to it and some mass that's oscillating up and down, and I move my hand suddenly, then it's gonna oscillate and then eventually come to a new steady state length. So this is a second order system instead of a first order system, where I have, and I believe, and again, maybe Rich would yell, or did you guys take system dynamics with Ritz or Campbell? That was too many noises for me to hear all at once. Raise your hand if you took it with Mark Campbell. Did I ask Ritz? No. Who else taught it that I don't know? Okay, I didn't realize he had taught it. Okay, I'm out of the loop. Anyway, so you have step input to a system like that. Now that you have two independent energy storage elements, so we have the spring and the mass that can kind of trade energy back and forth, your step input can look, oh, I messed it up, can look like that where you have oscillations. It doesn't always look like that depending on how much friction there is. So if there's a lot of damping, and we're not going to bother with damping ratio and all that, it can, I guess this is kind of a tricky thing where conceptually the step response of a second order system can look like the step response of a first order system, even though it's second order. Okay, so we have, again, that's your spring mass damper system. Let me check, because I had another pull everywhere question, but I don't know if we're going to get to it today, so I moved it to, yep, I'm going to move that to Wednesday. We have an analogous circuit called an RLC circuit. So again, be careful about the difference between a resistor, which is zigzaggy, and inductor, which is curvy lines. Or if you have a step change in voltage to this circuit, you can get kind of a similar response like this. We are not going to be doing that in detail in this class. I just kind of want you guys to know about it conceptually. That basically the point is that electrical systems can also oscillate, is the conceptual takeaway here. And when we talk about frequency response, which we're going to get to next week, or sorry, next Wednesday, but I kind of want to give a conceptual introduction to today. Again, for those of you who maybe, so again, raise your hand if you did not take system dynamics. Okay, put your hands back down. Raise your hand if you don't know what I'm talking about when I say frequency response. Okay, so those of you, okay, so we have a few. So those of you who didn't take system dynamics, did you learn about frequency response in 2213? Or did you learn frequency response? Or you just kind of intuitively think you know what that means? Liar. Okay. So for frequency response, again, I forgot to bring the slinky I would usually use for this demo, but imagine that I am just moving a slinky up and down, but now I'm changing the frequency at which I move my hand. So kind of starting out very slowly, and then eventually I'll try to steal one of my kids' toys at home and bring a slinky to demonstrate this on Wednesday. The x-axis is now frequency, and the y-axis is now some ratio of my output, whether it's two voltages or two forces, two positions, whatever. For a second order system, I'll get a resonant frequency, right? And again, this is intuitive for like pendulums, pushing somebody on a swing, moving a slinky, whatever. There's going to be some resonant frequency where you get the maximum output, and then eventually you start moving too fast, the output's going to kind of taper off and not really respond. Again, just like those of you who did take system dynamics probably spent a lot of time on this for mechanical systems and spring mass dampers. The point is that this can also happen with electrical systems. Okay, so really good example here is a radio tuner, right? You have a system where you want to be able to tune into a specific frequency and kind of ignore all the other frequencies, so you want a really, really sharp resonant peak. So you get a high response at the frequency you're at, and that is done, you can literally build a really simple little radio where there's just a big coil of wire and a sliding metal contact that changes the length of the coil, therefore changes the inductance. And you can make a little AM radio that can tune into local radio stations just by kind of knowing how this works and changing an inductor. So let me double check. Okay, we've got a little more time, so I'm going to get started on what we're going to do next time, and then we'll pick up more with frequency response on Wednesday. The other useful application here, we've kind of been talking about power supplies a few times now. Going back to the step response thing, so forget the frequency response stuff for a second, rewind a page to step response. I'll redraw that graph here. Remember, we have the step response of an RC circuit going like this. Again, when I popped the cover off that old cell phone charger last time and you saw the capacitors inside, one of the motivations for this is we have alternating current coming from a wall outlet, right? Which somewhat confusingly, we say AC a lot for alternating current, but a lot of times it also means alternating voltage. So the y-axis of this graph is voltage, right? That's what you would have. But again, don't do this if you hooked your oscilloscope up to a wall outlet. Okay, don't do that. But if you did, you would see an alternating sinusoidal voltage going positive and negative, right? To charge a battery-operated device, we need to convert AC to DC. Right? So you need to convert a sine wave to a constant. The first step there is a step called rectification, which we won't talk about until we get to diodes, but where we kind of convert the negative halves of that wave to positive, so we have just these positive parts of a sine wave, but that's still not constant, right? It's positive, but it's not constant. We need a third step. I'm going to draw this one in a different color, where if you feed this into an RC circuit, so it's not a square wave anymore, we kind of have this weird half sine wave input, what you're going to do is charge the capacitor up. But then when the input drops, again, the RC circuit has a time constant, so it takes time for the capacitor to start discharging, right? And then you hit the next bump, it charges it up a little bit, and it starts discharging again, and so on. So you can actually go look up the specs for a power supply, and you'll see sometimes something called ripple voltage listed. So it's not literally converting it to a perfect constant flat voltage, but it's pretty constant within some range, right? And if you buy, and I have some good graphs of this I'll show in slides either next time or maybe wait until we get to diodes. This can be the difference between like a genuine iPhone charger and the $1 knockoffs, right? If you hook up an oscilloscope and look at the output, again, there's a guy who did a teardown of like genuine versus counterfeit chargers. This graph just goes haywire on the cheap ones, right? So when you talk about like, hey, you should probably, whether it's a computer, phone, whatever, like don't buy really cheap, shady power supplies for your devices. That's part of the reason, is that they were just kind of did a shoddy job on the power electronics, and this voltage is all over the place. Okay, so we have a few minutes left, so I'm going to get started with the concept that we're going to do next. So I don't know why I keep saying next week, on Wednesday. Or sorry, let me pause there. Any questions on, again, this was a lot of conceptual stuff. Questions on any of this? Yes?
What is the practical consequence of ripple voltage? Is it like burn out of the battery, inefficiency?
So I think the question was, what is the practical consequence of ripple voltage? And I think the answer is it depends on what you are powering and how sensitive it is, whereas it might, again, for certain getting more into kind of microcontrollers and processors and things, what range they will actually work at. For example, USB, I think, is nominally 5 volts, but the spec is actually 4.75 to 5.25 volts or something like that. So if you have ripple voltage going outside of that range, then the device that is relying on a voltage within that range to function properly is going to start browning out or acting weird. In terms of just directly charging a battery, honestly, I'm not sure. There's more that goes into battery charging circuitry than just this, but I think in general rule of thumb is kind of higher quality, more expensive power supply is going to have you get closer and closer and closer to kind of a pure flat line. Good question. Okay. Let me switch to next page here. So our goal now is going to be to take our same RC circuit, measure V out, but this time instead of that step change from a square wave, V in is going to be a sine wave. Okay, and we want to know what is the frequency response, or what is the ratio of V out to V in as we change the frequency of this input sine wave. To do this, we are going to need to define a concept called impedance. And I guess when I say we are going to need to define, did you do impedance in physics? Raise your hand if you did impedance in 2213. It's kind of like the half, maybe sort of hand waves. Okay. This is a concept that you either love or hate because it starts bringing imaginary numbers into the game. And I think as the electrical engineering approach was like, hey, this actually makes the math easier. I think the mechanical engineering reaction tends to be like, what the hell is this? Like, we don't have imaginary newtons. Why are we talking about imaginary volts or ohms or whatever? So don't shoot the messenger. This is just kind of the standard in electrical engineering. And again, arguably does kind of make some of the math easier. So the symbol we're going to be using now, which again, I may skip drawing a lot of the time, but if you see this, the little circle with a sine wave inside it, that stands for an AC voltage source, where again, kind of obnoxiously, AC actually stands for alternating current. So if you read that out, it's alternating current voltage source, but again, that's just a convention in English, where again, that means I have a voltage that is oscillating about 0. So if I draw a source tied to ground like that, that means that sometimes the voltage up here is negative, and then sometimes the voltage up there is positive, sometimes the voltage up there is actually negative reference to ground, right? So if I say my V in, it has an amplitude of 10 volts, that means that this voltage as reference to ground is going between plus and minus 10 volts, which I think kind of gets kind of counterintuitive sometimes because we're so used to thinking of batteries and DC voltage sources where that voltage is just always positive relative to ground. Okay, and I'm not going to get into the impedance stuff because that takes too long to explain. We are going to need to remember Euler's identity. I'll jot this down really quickly because that's one thing you can do between now and Wednesday is start to remember complex algebra slightly. So if you remember that equation and you have the real and imaginary plane and you can represent a point in polar coordinates either in Cartesian or polar coordinates in the complex plane. We'll do a quick refresher on that at the beginning of next lecture, but like jog your memory on that in the next 48 hours if that doesn't look familiar. Okay? That is it for today.